You're welcome. Good evening to everyone. And my name is Fatih Şirin from ULAKBİM University. I'm a lecturer in this university. And this evening, I want to talk about one spectral problem, actually. Actually, for this work, we want to prove basicity properties for eigenfunctions systems for one discontinuous problem, spectral problem. And actually, firstly, we start from spectral problems. And you know, in many questions of mathematics, mechanics, or physics, spectral problems play an essential role. Actually, when we want to solve a problem, for example, or a physical problem, and by using Fourier methods, then we find spectral problems, actually. And here, when it comes to our problems, this problem comes from a vibration problem for a string. Actually, this string fixed at both ends, and with a mass in the middle. When we solve this problem by using Fourier methods, then we find this problem, actually. And here, the important situation is that lambda, meaning that spectral parameter is in both equation and condition. So if we want to solve this problem, actually, if we want to find eigenfunctions, and if we want to prove the basicity of eigenfunctions, then we should use direct sum space. Firstly, I want to talk about this problem. Actually, this problem was worked by Telman Gasimov and Bilal, actually. And since 2006, this problem this problem is worked, actually. Yes. Here, when we want to find eigenvalues and eigenfunctions for this problem, we can find these series. And the first series is basic eigenvalues, but the second one is actually, the second one has asymptotics. So if we want to find eigenfunctions, then we should find asymptotics for eigenfunctions, especially the second one, U2n, like that, you see like that. And here, if we want to prove basicity properties for these series, then we should use a new methods. In these years, actually, there are two different methods. The first method is basic criteria, and this is related to actually when we want to prove basicity of this eigenfunction system, then we should show that this system is complete and minimal, and the projectors for these systems should be uniformly bounded. These three criteria is enough for basicity of these systems. But actually, we work on this problem in Grant-Lebesgue space, I will show which one is important for us. I will show that. But here, firstly, we define our problem in Banach function space, and actually, this problem was studied on Lebesgue space, Morey space, and weighted Lebesgue space, actually, and Grant-Lebesgue space, and weighted Grant-Lebesgue space. The last two space are actually was worked by us, and so here, what is the meaning of Banach function space? Actually, Banach function space is general space. For if we want to give an example, if we want to give an example, we can give Grant-Lebesgue space for the Banach function space, or classical Lebesgue space. Yes, I mean Morey space can be, and like that. So we want to work on this space, Banach function space, because Banach function space is a general space. Let's look auxiliary facts. The first definition is related to P clause and P basis. Actually, these definitions are important because the second method is related to these definitions. And the second method is that when you have a system, but the system is not non-standard. Actually, the system is non-standard. And if you want to prove the basicity properties for non-standard systems, then you can use classical systems. For example, trigonometric systems. For example, exponential systems. These systems, for the basicity properties of these systems, actually can be shown easily in standard or non-standard space. So let's define it. If the system UN from Banach space, X Banach space, is called P basis if it's satisfied this condition. Actually, after this is P basis, but here the condition is that the UN should be basis in X. And next definition is related to P clause. Here there are two systems, and these systems are P clause when this condition is satisfied. Actually, after that, we can give the second method. This is a new method, and this method comes from yes, four years ago. Actually, I can say that by Bilarov and Telman Gasimov. So here, when X and P basis in X and yn is Q close to Xn, and here P 1 over P plus 1 over Q equal 1, actually, then the following properties are equivalent. The properties is that here Yn, actually, I can say that Yn is a simple system. For example, trigonometric system and exponential system it can be. And here Xn is a trigonometric system, meaning that is an easy system, basic and simple system, sorry. And Yn is our systems that prove that want to prove basicity properties. So here, if Yn is these properties are equivalent. What is the meaning of that? The meaning that if we prove one of these properties, then other ones are true, actually. So in general, we denote Yn is a minimal system. When we denote that, meaning that minimal property, then after that we can say that Yn is a basis in X, Banach space, X Banach space. So we will use this theorem by showing basicity properties of our eigenfunction system. So let's talk about Banach function space. What is the meaning of that? Firstly, we can give a Banach function norm by using this definition. And here, n plus be the cone of mean measurable functions. And here, R can be real number. R mu is be a measure space. So for definition, if these properties are satisfied, then rho from n plus to this interval actually is called a Banach function norm. This is a Banach function norm, and after that we can give a Banach function space definition. Let rho be a function norm. The collection X, all functions f from M, and rho f absolutely. And here there's actually this is not important. Absolute value meaning that module. We can give a module, but this is true without module. Actually, there's no problem in some operations. This is important for us in some basic operations. And so let's talk about Boyd indices. The Boyd indices are important because this embeddings is very important for us. Because when we talk about, actually, if we talk about basicity properties for any systems, then the space should be separable. But here we will see that X is not a separable space. So we should find a separable subspace. But for the separability, for the property of separability, we should use this embeddings. Actually, continuous. It should be continuous embeddings for the proving our steps, or some steps. So you can find for the more details, you can use Banach Sharpley books, and I will show in reference again. So yes, density criterion is very important because we want to take a separable subspace. And here, let's define XB. XB consists of simple functions, actually, from X. Absolutely, the close in X of the set simple function is denoted by XB. And here we have a lemma. Lemma is that X be an rearrangement in invariant space on R, and XB be a closure of simple functions in X. Yes, this lemma is important for us because we will use T delta, meaning that shift operator. When we define a suitable subspace, meaning that separable subspace, we will use T delta, T shift operator. And here this lemma gives us the equivalence between XB and XS. We will say this space XS actually by using T delta, by using shift operator. So let's pass main results. And here, for the separable subspace, we should use shift operator T delta like that. It's defined like that. And here we denote this subspace by XS. XS is the closure of X in X of a linear manifold of a function of functions from F that satisfy this condition. After that, we can give density theorem because when we define a subspace, we should prove the property of separability for XS actually. So this theorem is that X be a function space, then infinity differentiable function space is dense in XS. We can show this. We can show this density property by using continuous embedding from lemma, if you remember that. Yes. Here, let's pass the basicity properties. But firstly, we should show classical system, the basicity of classical system, meaning that sine NT system. And here, actually, we can show cosine NT by using same process, same proving, but we don't need to show cosine. We only use sine system. So here we should for the easily proving of this lemma, we should use this interval instead of -1 and 1, because if you remember our problem, for the domain of our problem, the domain of our problem is this interval, -1 and 1. We will use this interval, but firstly, we should use that one for the easily proving again. And here, let X be a function, Banach function space, and the domain is this interval. Be a rearrangement invariant Banach function space with the void index alpha X, beta X between 0 and 1. Then the system sign form a basis in XS. Actually, we can show for this interval again. We can show that. So this lemma is true, absolutely. The proving of this lemma actually by using simple methods. You know that simple methods for the basicity operation. For the basicity, you should find actually for any function from Banach function space, we should find some constant for some coefficients for sine and t system, and Fourier actually comes from Fourier series from here. Then this is very easy proving for this lemma. So we can pass the next theorem. If we want to prove this system, the basis of this system in XS minus the interval from minus p to p, then we can separate like that by using direct sum. Then absolutely from this lemma we can show easily this system forms a basis in XS. After that we can talk about now basicity of eigenfunctions comes from our problem, our spectral problem 1, 2. You know that, you can remember that. In x minus 1, between minus 1 and 1, direct sum, complex number. Actually, why we use direct sum space? The question, actually, the answer of question is that when we create linear operator for this equation, for this boundary value problems, then we should use we should use this direct sum space because spectral parameter is in both equation and boundary condition. So when we create a linear operator comes from spectral problems, then we should use this space. So firstly, we should prove the basicity properties of eigenfunctions in this space, in direct sum space. After that, we show only x, the space of x, only space x, the Banach function space. Yes, the theorem is that actually this condition comes from lemma. If this condition is satisfied, then the lemma gives us continuous embedding. Actually, continuous embedding is very important for us. So let's X be a rearrangement in my Banach function space, and its void in this alpha x with beta x satisfy this condition. So U0 and UIN, these comes from eigenfunction systems of spectral problem, forms a basis in XS plus C, direct sum actually. And after that, after that we will prove only in X, in the space of X. And here I can talk about some reference. The first one, Gasimov and Mammadova give us these spectral problems. They calculate eigenvalues, eigenfunctions, and after that they showed basicity properties in Lebesgue space. And the second reference is related to new methods for the basicity. New methods is that P close, P basis, P close systems, and by using these definitions, we can give a theorem for the basicity of non-standard systems. And the third one is related to Banach function space. Some details in here for the Banach function space. And the last two reference, actually, we work on ground Lebesgue space and weighted ground Lebesgue space for these problems. And thank you for listening to me.
Evet, Profesör Şirin.